Welcome to this explainer. Today, we're going to look at the universe through a slightly different lens. Instead of just admiring the pretty lights in the night sky, we're going to treat the galaxy as a finely tuned machine, a really complex, massive orbital clockwork. And, like any good engineer, once we understand how a system works, we're going to subject it to a cosmic stress test just to see exactly how it breaks. So let's dive right into this by asking a foundational question for our system resilience test. Exactly how much gravitational interference can our orbital clockwork withstand before total, catastrophic structural failure? A galaxy is this incredibly delicate, balanced system of millions of stars all orbiting a common center. But what happens when a massive rogue object, like a wandering foreign mass, say a black hole, just drifts right into that fine-tuned balance? Well, here's our blueprint for today's explainer, mapping out the exact sequence of the stress test. We'll start with the cosmic vacuum fallacy, calculate the Hill sphere, look at the gravitational tug of war, check out slingshots and gravitational waves, examine the quasar power plant, and finally test our overall cosmic system resilience. Okay, Section 1, the cosmic vacuum fallacy, debunking the suction myth. Before we can break our system, we absolutely have to correct a fundamental engineering misconception about how foreign mass actually behaves out there. There's this stark contrast between the sensationalized vacuum cleaner myth you see in sci-fi and the actual orbital clockwork reality. Pop culture treats black holes like these giant cosmic vacuums just actively sucking in the universe with infinite reach. But a vacuum cleaner works using air pressure. Gravity doesn't work that way. The reality is that gravity is strictly a distance-dependent, attractive interaction. If our sun were magically replaced by a black hole of the exact same mass right now, Earth wouldn't be sucked in. Our orbit would remain perfectly stable. It's literally all about mass and distance. Moving on to Section 2, calculating the Hill sphere, defining the limits. Let's look at the exact mathematical boundaries where our system stays stable. To understand this, we use a concept called the density of influence. The Hill sphere is the exact spatial region where an astronomical body's gravity is the absolute dominant force. Think of it as a gravitational safe zone. If a star is comfortably inside its host galaxy's Hill sphere, it follows that galaxy's rules. But if a massive rogue object approaches, its own Hill sphere starts to overlap and actively compete with the galaxy's grip. To put this into perspective, a black hole might be physically tiny, we're talking maybe just a few miles across in some cases, but its sphere of influence is enormous. Take our sun, for example. Its maximum unstable Hill sphere extends a massive 230,000 astronomical units. That totally proves that a physically compact object can cast a giant gravitational footprint, disrupting the finely tuned orbits of nearby stars way before making any physical contact. Which brings us to Section 3, the gravitational tug-of-war structural failure. So, what actually happens to our galactic machine when a foreign mass breaches those limits? This is where the stress test gets catastrophic, and the crucial concept here is tidal force. Because gravity weakens with distance, the side of a star cluster that's facing the rogue black hole gets pulled way harder than the far side. Visually, the object is physically stretched out of its round shape into a phenomenon that astrophysicists literally call spaghettification. It's not a gentle nudge, it's a severe, violent gravitational tug-of-war that actively overrides the internal self-gravity holding those stars together. We can track this mechanical failure in 3 distinct steps. Step 1, the rogue object makes a close pass, drastically increasing that tidal gradient. Step 2, the host system's material stretches so far it overflows its gravitational boundary, what we call the Roche lobe. And Step 3, the system's grip is overpowered entirely. We call this tidal stripping. Instead of neat little orbits, the stars are violently drawn out into these long, chaotic leading and trailing stellar streams. The structural integrity is officially compromised. All right, Section 4, slingshots and gravitational waves, ejection dynamics. You see, a machine doesn't just break, its parts have to go somewhere. And this chaotic rearrangement perfectly debunks that no-escape fallacy we talked about. The rogue black hole doesn't just swallow all these stars. Actually, most stars completely escape that fate. While some stuff is consumed, much of the clockwork is just violently rearranged. Stars get flung into new, highly elliptical orbits. Even crazier, some get caught in a gravitational slingshot, gaining so much kinetic energy, they're fired out of the galaxy entirely as hypervelocity stars, traveling at thousands of kilometers per second. But stars aren't the only things getting kicked around here. If our foreign mass happens to be a pair of merging black holes, we have to factor in gravitational waves. These are literal ripples in the fabric of space-time caused by the extreme acceleration of massive objects. And when these waves are emitted unevenly, they generate a massive physical recoil force on the black hole itself. A fantastic real-world example of this is the GW 190412 event. The asymmetrical gravitational waves from this specific merger produced a physical kick that surpassed 50 kilometers per second. Think about that amount of kinetic energy. It was powerful enough to eject the newborn black hole entirely from its host cluster. So, wild it sounds, the disruptor that broke this system can actually be violently kicked out of the system itself. Section 5 now. The Quasar Power Plant Cosmic Spotlights. For this final test phase, we're looking at the ultimate byproduct of a compromised system. We're talking about how a failed, shredded gravitational encounter actually turns into the most efficient power plant in the universe. Turning that shredded debris into a quasar, a literal cosmic spotlight, requires three main ingredients. First, you need a rapidly spinning supermassive black hole to act as your gravitational engine. Second, a bright corona of hot gas emitting intense X-rays. And third, incredibly strong magnetic fields threading that corona to drive the powerful jets. When these three align, it's a phenomenal light show visible across the universe. And what's truly mind-blowing is the sheer efficiency of this setup. Just look at these numbers. Standard nuclear fusion, the very process powering our sun, converts about 0.7% of its mass into energy. But the friction and gravitational stress of an accretion disk falling into a black hole, that can convert up to 32% of a mass into pure energy. It absolutely dwarfs the output of standard stars, emitting radiation so intense it easily outshines its entire host galaxy. Finally, Section 6, Testing Cosmic System Resilience, the Engineering Verdict. So we've seen the myth, the tidal stretching, the ejections, the massive energy output. Now let's synthesize all this. Astrophysicists who model these things have a saying: tidal stripping increases the internal energy of bound systems, preferentially stripping low-mass stars from extended halos over timescales of hundreds of millions of years. In engineering terms, it means the destruction isn't an instant explosion, it's a cumulative energy injection. The gravitational interference systematically and quietly dismantles the system over eons by stripping its most vulnerable, loosely bound components right at the edges first. Ultimately, a galaxy maintains its structural integrity only as long as its internal binding energy can outlast the intense, localized tidal stresses of these rogue foreign masses. It's an ongoing, delicate math equation, constantly balancing internal self-gravity against external interference. And once that tidal stress permanently exceeds the binding energy, the clockwork shatters into a chaotic stream of debris. As we wrap up this explainer, I really want you to consider this. Current data suggests there could be roughly a dozen rogue, supermassive black holes drifting just on the edges of our own Milky Way right now. They emit no light, they just carry their massive spheres of influence silently through the void. So with that in mind, which finely tuned cosmic clockwork is about to face its ultimate structural stress test next?